Welcome to Module 5 on signals and frequency. We'll start with sinusoids and phasors. A sinusoidal signal is described by the equation x of t equals a sine of omega t plus phi. Let's explore each parameter. The amplitude a determines the peak height of the sinusoid. A larger amplitude means a taller wave. The angular frequency omega determines how fast the sinusoid oscillates. Higher omega means more cycles in the same time period. The phase phi shifts the sinusoid left or right in time. A positive phase shifts the wave to the left. A phasor is a rotating vector in the complex plane that represents a sinusoid. The angle increases with angular frequency omega. As the phasor rotates, its imaginary component traces out the sinusoid. This connection between rotation and oscillation is fundamental to signal analysis. Now let's see how complex numbers save electronics in video 5.2. In AC circuits, impedance Z equals R plus Jx, where R is resistance and X is reactance. The J represents the imaginary unit. We can visualize impedance as a vector in the complex plane, with resistance on the real axis and reactance on the imaginary axis. Euler's formula states that e to the j theta equals cosine theta plus j sine theta. This magical equation connects exponentials to rotation in the complex plane. On the unit circle, e to the j theta is a point at angle theta. Its real part is cosine theta, and its imaginary part is sine theta. In AC circuits, we represent voltage and current as complex exponentials. This makes calculating impedance much simpler than using trigonometry. Imaginary numbers aren't just mathematical tricks. They represent real physical phenomena like phase shifts and energy storage in reactive components. The J indicates a 90-degree phase relationship. Now let's explore frequency response in video 5.3. Frequency response describes how a system responds to different input frequencies. It's the ratio of output to input as a function of frequency. Gain is the magnitude of the frequency response. It tells us how much the system amplifies or attenuates signals at different frequencies. Phase shift measures the time delay between input and output. The output signal is shifted in time relative to the input. Bode plots show frequency response on logarithmic scales. The magnitude plot shows gain in decibels, and the phase plot shows phase shift in degrees. Here's a low-pass filter's magnitude response. It passes low frequencies and attenuates high frequencies. The cutoff frequency is where the gain drops by 3 dB. The phase response shows that low frequencies have zero phase shift, while high frequencies lag by 90 degrees. At the cutoff frequency, the phase is minus 45 degrees. In Module 5, we learned that sinusoids are fundamental signals described by amplitude, frequency, and phase. Complex numbers and phasors simplify AC analysis, and Bode plots help us visualize frequency response.